This is problem 13-146. A boy throws a ball from a window 10 meters above the ground as shown in the figure below. The initial speed of the ball is 10 meters per second. The ball has a constant downward acceleration of 9.81 meters per second squared. A second boy runs along the ground at a speed of 5 meters per second and catches the ball on the run. Determine A, the distance x at which the boy will catch the ball, and B, the relative velocity v b relative to a of the ball with respect to the boy when he catches the ball. Okay, so a couple things to point out here. Is first that I find that these problems finally start getting kind of interesting because now instead of just where's the ball going to land, it's a second boy runs along. And you now have to take into account the fact that the ball is moving and it is moving towards another object that has a relative velocity. And speaking of relative velocity, that is what this term is talking about. I say velocity of B relative to A. All right, so we're going to be using this term very, very much from now on in the course. And this is our first chance to start understanding how this term works and what we do to use it. And there are a lot of very interesting little variations of how you can plan for utilizing this term. So let's take a look at the problem. All right, so let's first talk about some of the given information. So we know that the height of the ball is 10 meters, and I'm just going to draw the ball starting here. Okay, and then so we'll have h equal to 10 meters, and then the initial speed of the ball is 10 meters per second. So there's going to be this initial velocity of 10 meters per second. Okay, and the acceleration is downward at 9.81 meters per second. So how we could treat this is, instead of just writing the number, start getting used to downward being negative and in the j hat direction and turn this into a vector. Like right away, let's start thinking of all of our accelerations, velocities, and positions as vectors as often as possible. Okay, and then the second boy runs along the ground at a speed of 5 meters per second. So we could say the velocity of the, I guess I'll call it, boy. Well, because there's ball. So we'll just say A. I'm just gonna have to label like the picture does that there is an object A, and then there's the object B, which is the ball. Okay, so then he catches the ball on the run. Determine the distance x at which the boy will catch the ball. So there's going to be some unknown x where the ball and the boy will meet at the ground at zero height. All right, well, how are we going to approach this problem? Let's see here. Oh, let me write in the 5 meters per second so we know what's going on. All right, well, we already have our acceleration vector. So why don't we create our velocity vector? So the velocity of the ball is going to be, we threw the ball at 10 meters per second horizontally, and we're going to neglect air resistance. So that means that there's nothing that is going to slow the ball down in the horizontal direction. And I am only talking about the horizontal direction when I'm talking about this 10. Okay, and so then we have the j hat direction, and in order to get the j hat direction velocity, we're going to integrate the acceleration that only has a j hat term. So if we integrate the negative 9.81, then we'll get negative 9.81 t, and this is in the j hat, and now this is meters per second. Okay, all right, now let's get a position vector. So we're going to integrate again, and we'll end up with 10t in the I hat direction. Now, what is the initial position? That's a good question. We're talking about the horizontal. So in the horizontal, we're going to start at 0. So the plus c will be 0. The initial condition of the x direction will be 0. And then plus, we're going to have to integrate the negative 9.81t to be negative 4.905 t squared. So it's 9.81 divided by 2, and then there's the t squared. And then the initial height is in question right here. Well, we're going to start up at 10 meters if we consider the ground as 0. So then plus 10. Okay? And then this is in the j hat, and the units are meters. Okay, so we have an acceleration vector in both I hat and j hat. It's just I hat is 0. We have a velocity vector in the I hat and j hat components, and we have the position vector that has I hat and j hat components. All right, let's see what we can figure out. So we want the distance to be known in the horizontal when the boy and the ball meet. Now, another thing is we have to assume is that the boy started at the ball, or sorry, at the wall is what I mean to say. Okay, like we don't necessarily, they don't say that explicitly, but assume that, like, I don't think they do. There's a ball from the window. Yeah, they don't tell you where the boy on the ground starts. We're going to assume that the boy starts at the wall. And so basically we have to figure out, where does the boy have to be in order to catch the ball? Well, the boy has to be where the ball is when the ball gets to the ground. So in a sense, it actually doesn't matter where the boy started, as long as the boy gets to the ball at the point where the ball gets to 0 height. Okay? So how do we find out where the ball is when the ball is no longer above the ground and actually reaches the ground? We can take the j hat component of the position, and we can find out when that j hat component becomes 0. So how do I do that? Well, we say 0 equal to only this term, negative 4.905 t squared plus 10. And we solve for t. So t is going to equal 1.43 seconds. Okay. And now we have to find out where in the x the ball is at that time. So now we take the I hat component and we solve for basically RB in the x is equal to 10 times 1.43 seconds. And that equals 14.28 meters. Sorry, I have 14.28 because I actually wrote out more digits, and I decided to round my digits a little sooner than when I wrote on the whiteboard than when I worked out the problem. So forgive the fact that this should actually be 14.3. All right, and so next is part B, though. So that was part A. At what distance x will the boy catch the ball? Right? Now, find the relative velocity of basically the ball relative to the boy. The velocity of B relative to A. B is the ball, A is the boy. The ball with respect to the boy when he catches the ball. All right. So, like, the ball is coming down towards the boy, and if the boy is running at 5 meters per second, then the ball meets the boy, and there is a relative velocity between the two of them. So here is the equation. The velocity of B relative to A is equal to the velocity of B minus the velocity of A. Now, real quick, I want to point out where that equation came from. So that equation is coming from equation 1329 on page 75 of the textbook. However, it doesn't look like what I have, because I had v of b relative to a equal to the velocity of b minus the velocity of a, right? But that's not what's written in the book. The book has it rearranged. All right, so obviously, or at least I hope it's obvious, that all I did was just do a little bit of algebra there. But let's look at this equation as it is. Basically, when they do the position vector, they're looking at figure 13-37, and they're saying, hey, if my position is, if I have a reference of the origin, and I want to know where B is relative to the origin, then this is the position of B relative to the origin, or B relative to O. All right, and then I have the position of A relative to O is just this vector here. All right, so that means that there is also a vector that is B relative to A. And we can just add the A relative to O plus the B relative to A and get to the same location as B relative to O. It's just a triangle. There's nothing fancy going on. It's just vector addition. All right, and all they're doing is just differentiating. All right, so then if you take the derivative, then you get the velocities. And if you take the derivatives again, you get the accelerations. To me, this is either just really obvious or not very explanatory. It depends on like what kind of thinking you tend to have. Okay, if like that math just is like kind of like, oh yeah, duh. I mean, if it's the position vectors and they make a triangle, then you add the vectors up, and that makes sense. And then you just take the derivative. All right, fine. I also have felt personally that it was a little dissatisfying when I first looked at this, that the velocities would just be another triangle, the accelerations just be another triangle. But hey, that just is what's true. And it will, for those of you who are a little dissatisfied with that and they kind of feel like, yeah, okay, I guess so. Wait till you see it in action. I think that you might be the type of person that when you see problems worked out and see that it actually works, this will actually be a little bit more exciting and satisfying. So let's go back to the problem now that we know where that equation is coming from. Okay, so now we have to figure out how to deal with these vectors. So we want to find the velocity of the ball relative to the boy. Okay, well, it's the velocity of the ball minus the velocity of the boy. So we just need those values. Well, what's the velocity of the ball? The velocity of the ball as a function of time is this equation here, this function, right? So, however, we care about when the ball is caught. So we know that we have 10 I hat all the time. And then we also know that we are going to have negative 9.81 t, and the ball is caught at time 1.43 seconds. And this is a j hat term. Then, so that's just b. That's the velocity of b. All right. Now, velocity of A. Well, we know that velocity of A is the boy running 5 meters per second to the right, which is positive, and only in the I hat direction. Okay, then we just do the algebra. However, let me make sure that I write the correct sign, because it is minus the boy running to the right, because it's minus VA. So don't mix that up. Don't make the mistake that I just made there for a second. Okay, so then we do the algebra and we get 5 I hat. You only add and subtract the I hats with each other and the j hats with each other, and then minus the 9.81 times the 1.43, which is 14.03. And this is in the j hat direction. And that is the velocity of the ball relative to the boy, right there. Now, you can find the magnitude and the direction if you want. Personally, for me, if you're taking my exams, this right here, I already feel like is having done the analysis. So for grading, for my grading, for the oral exams, if you get to this I hat, j hat value, you can stop. As far as I'm concerned, you have done the analysis. I don't care about doing the vector algebra after the fact.